Okay, let's take a look at a geometric series now that we've had a look at what an infinite series is and how to find the partial sums, a technique that will come in handy for us later. Let's take a look at a geometric series. A geometric series is a series of numbers where the terms take on this form: a constant, times r, a ratio, so it's a fraction, to the n minus 1 power. And so when we see this pattern, we know right away we have a geometric series. Now, why might we want to identify a series as geometric? Well, that's simple. Once you know you have a geometric series, there's a very easy rule which determines whether the series converges and what value it converges to. So we'll get to that when we get a little further down. But that's the real reason we're interested in. We would like to fit our series to a geometric series if possible, because we can easily know the answer to our key question: does it converge? And if it does, what does it converge to? Okay, let's take a look at an example. So suppose I were to write the series this way. I write out this series of terms. Okay, and we could keep that pattern going. You might be able to recognize the pattern already. Maybe you don't. I don't know. So what we want to do here is we want to try to make this sequence of numbers fit into this pattern. We want to be able to write that a sub n term in this format. So we want to find if there's a common factor that could go to the front of each of these terms to be the a. And then we want to find a ratio that could receive the power n minus 1 to produce these values. So the only common factor I see between 1/8, 1/4, 1/2, and 1 is 1. So I'm going to guess that the a might be 1. So if this is my a, now I need to find my r candidate and see if the n minus 1 power fits. So if my a is 1, then that gives me a 1/2. Now, the 1/2 right here in the second term, in this second term, n minus 1 is going to be 1, so that would be r to the first. So the 1/2 looks like a good bet right there. Let's see if these other terms fit, because for my first term in the series, I would have a 0. When n is 1, I would have 1 times 1/2 to the 0 power. 1/2 to the 0 power is 1 times this 1, that's 1. When we go up to our second term in the series, 2 minus 1 is now my power. 2 minus 1 is 1. 1/2 to the first power is 1/2, times 1 is 1/2. When we go up to the third term in our series, we now have 1/2 to the 3 minus 1 power. 3 minus 1 is 2. When we square 1/2, we get 1/4 times 1. So it looks like we're in good shape. Let's check the fourth term. 4 minus 1 would be 3. 1/2 cubed would be 1/8 times 1. So this looks like our situation. We have this geometric series if we say let a equal 1 and r equal 1/2. So now we know that this series is geometric. So the series is geometric. And you can write it this way. Right there. So we now know that we have this series of terms, 1 plus 1/2 plus 1/4 plus 1/8 and so on. If we let a, the constant multiplier, be 1, the ratio is 1/2, and we get this series of terms. So we now know we have a geometric series and it's written this way. All right, so that's great. And what we know now also is we have a theorem presented to us in the book that says a geometric series converges. So this is going to converge if the absolute value of the ratio is less than 1. So let's check up here. Is the absolute value of 1/2, our ratio, less than 1? Yes, it is. Okay, so we now know that this geometric series converges because it passes the rule or the test for convergence of a geometric series. Is the absolute value of the ratio less than 1? If it is, then it converges. Okay, now the other thing we know from this same theorem that tells us about convergence is that this converges if the ratio is less than 1, and since it is, we also know that it converges to, we say it converges to a over 1 minus r. So in our case, a is 1 from right up here, and then r is 1/2, so 1 over 1 minus 1/2. So that would be 1 over 1/2. And when we invert and multiply, we see this converges to 2. So when we add up all of the terms in this geometric series going all the way out to infinity, we're going to end up with a total of exactly 2 if we can go far enough. Now that's the great feature of finding a geometric series, is that you can start with a basic list of terms that are being added together. If you can identify that as geometric in form, you can apply this very simple test, compare the absolute value of the ratio to 1, and if it passes that test, as our example did, then you know it's going to converge to a divided by 1 minus r, which in our case turned out to be 2. So often when we're working with infinite series in general, we're going to try to take this same kind of approach to fit our series that we're interested in into a common format where there's an easy test available to determine if it converges. That's in fact going to be the bulk of our Chapter 9. So thanks for stopping by and checking out the geometric series. If you'd like to see another example or two, I'm going to put those in another video here in just a minute. Thanks.